Now, as discussed in the last session, we have our sigmoid function and we know how to use the sigmoid function, right? So what are we going to do now? We need to find these parameters and, so what are these parameters? And please bear with me, guys. My voice is a little bit cracky right now because I have a bad throat right now. So please bear with me, right? Okay. So we have our hypothesis function as hx, which is equals to 1 upon 1 plus e to the power minus m transpose x, right? So this is our hx, this is our hypothesis function which we talked about in last video. So now what our target is, we need to find this, this m here, right, in our function, such that m is the best fit line. So in our graph, m is the best fit line and our cost, which is the error, is minimized. Now how do you define this, which is error function? How do you define this error function now? The relation or the difference between the prediction, the predicted value, and the actual value, the actual y is, or the ground truth, which we call in machine learning terms is ground truth y, is what defines our function, the error function, right? So e as a parameter of h, xy, h of x and y is our error function, right? And in case of linear regression, what was this error function? If you guys remember, if you guys don't remember, then please watch the videos which are lined up in this playlist back. So please watch these videos. I'll go a little back to move a little forward, right? So just do that. In case of linear regression, what was our error function? It was e of hxy equals to, or this function was sigma of yi minus h of xi whole square sigma. So taking all the training data points, which was this function. I think it is visible. Yes, so it is visible. So this is yi minus hxi ka whole square, and there is a summation from 1 to m, right? So now the error function was completely fine, right, in linear regression. When your hx of I, this part, hx of I was just m transpose x, right? But now here it is a little complicated, because for this hx, if we use same error function, then it creates problems. The problem here is that if we have too many local minimal points, right? So suppose this is the graph and here we have too many local minimal points. So now what would happen would be, then the gradient descent would stop on the first local minima it encounters. So suppose it starts from here, it would go till here, right? It won't go beyond that. So we need to change this error function. So we need to change this error function, we need to modify it, we need to do a little bit modifications. Also, there should only be one global maxima or minimum, right? So we need one global maxima or minima, right? So now what we do is, now we distribute our problem into two equal parts. So let's just distribute our problem into two equal parts. That is okay, it is visible. That is y equals to 1, or y, okay, so y equals to 1, otherwise it is 0, right? These can be the two classifications, right? In binary classification, these are the two classes we have. Okay, so now what we want this to be, we want this to be as, so I'll write over here, what we want this to be is e of hxi and yi, the predictions, should be equals to minus of log of hxi when y equals to, okay, so I'll write on a fresh page so it's more clear to you guys. Because now what we want this to be is e of hxi I comma yi is equal to, should be minus of log of hxi, this is the x part, right? One part when y is 1, and for y equals to 0, we want this to be minus of log of 1 minus hxi. right? This should be our error function, modified error function. Now, now what would this function look like? This complete error function. Now, what would this look like? So in case of 1, you see this case, right? So take this case. So in case of when y equals to 1, so in case of when y equals to 1, suppose if hx is also 1, right? So let's say this complete value goes to 1. Then what would be minus of log of hx minus of log of 1 would be 0, right? So the error function at this point would be 0, and so let's see it graphically. The graph would look like a little this, right? So let this be our graph, and when y equals to 1, our error function would be minus of log of hxi, right? And it would look like, so suppose here we have our error function and here we have our hx, and this is the 1 value, so it would tend to 0 and the graph would look a little bit like this, right? This is the shape of our error function graph for in the case of when y equals to 1, right? Okay, so for the case of y equals to 0, our graph would look like this. So here we have e and hx, and this is a 1, right? So this graph would start from here and go like this, right? This is the asymptote. Okay, fine. So the graph looks a little like this, fine, in the case of y equals to 0. So basically what you are saying is that for any training data point, the error should not go in other direction. What we really mean is, if it is supposed to be 1, then it should stay close to 1, and if it is supposed to be 0, then it should stay close to 0. In a simplified form, if we combine both y equals to 1 and y equals to 0, what would our error function would be in this case? Let's see. So the combination of both the error functions would look like e of hxi comma yi equals to minus of log of 1 minus hxi. Let's take this y equals to 1 first. So minus of log of h of xi. This is in the case when y equals to 1, and minus of log of 1 minus hxi in the case when y equals 0. So that's what we saw right now, and if we just combine both of them, then the error function would look like minus yi log of hxi plus, or eventually it will go minus, so let's keep it minus 1 minus yi log of 1 minus hxi. Correct? This would what it look like on combination, right? So this is our error function, this is our complete error function, right? Fine. Okay, so this is our complete error function. So error function on whole training data would be, see, after taking the average, this would work on complete training data set, right? So we just need to take the average. So what we'll do is, I'll just remove the equal to sign, and in this whole function we would first do summation of all the training data points, and then because this number will become too large, so to normalize this, we will do 1 by n. I think this is clearly visible. So this is kind of a modification we use, right? This is the summation on all the training data points, right, which will be given in your data set, and to normalize this number we use 1 by n. So we are finding average error per training data point. So this is our final error function or cost function which we'll be coding for logistic regression, right? So I'll see you guys in the next video. If you like this video, then please hit the like button. If you haven't subscribed to the channel, then please subscribe to the channel, and if you don't follow me on Instagram, then please do follow me on Instagram. Bye.